Greetings and salutations, folks. We are back at the bench today, and we are going to be doing part 2 of the analog meters videos. And for those of you who haven't seen this before, I did a part 1 on voltmeters, analog voltmeters. And part 2 is going to be on analog amp meters or ampere meters that show you amperes. But I do want to make something clear that pretty well all amp meters are actually DC voltmeters, which of course then you can use a DC voltmeter in part 1 as an actual amp meter to indicate amps. Now you would have to, of course, change the scaling of the meter, and that can be done with software that is available. And I'll put that link in the description to that particular company that produces that software that allows you to rescale your meter with a printout, a laser printer or dot matrix, not dot matrix, bubble jet or something like that printout. So that'll be in the description. Okay, so I don't have a full set of different type of meters. These are the ones that I've had in my shop now for a period of time. I've obviously used a few over the years in building equipment. But there are other types out there. For instance, I do not have a null meter. A null meter would be where the needle here is actually in the center. And it would be really nice if that focused. There we go. Where the needle would actually be in the center. So now you could read either one side or the other side of 0 in the middle. Null meter. I don't have a null meter. But in another segment, I will show you how to use one of these meters as a null meter by biasing the meter to the middle. Okay, I'll also show how this can be used with a bridge circuit, and basically that's what it would be. It would be a bridge circuit that is biasing the meter to the middle so that we can get needle deflection on both sides of 0. So we'll do that in a future segment. However, let me zoom this out a little bit so we can talk about these, and I can show these to you. So what we have here is we have basically our standard meters that you can purchase from Amazon. I've used several of these meters. I have several of these meters sitting up on the shelf. If you'd watch part 1, you'd see that I have voltmeters of the similar type. This one is an 85C1 case style. So the voltmeters and the amp meters look exactly the same. This particular one, which is very nice, is that, and I'll zoom this up a little closer, it shows the resistance required, or the voltage required to give you full scale deflection for 50 amps. Notice it says 75 millivolts, and it's giving you a little picture of that being taken, that voltage drop being taken across a resistive element. Those resistive elements are commonly called shunts, and I'll show you a few in a few moments. Okay, some amp meters do not give you that shunt value for full scale. So we're also going to be looking at that and determining how we can get what voltage is required to provide a full scale deflection on this meter. Having said that, I will also show you how you can change that full scale reading per the voltage and current being fed into the meter, so that you can, instead of reading 50 microamps, you can actually use this meter to read, let's say, 50 milliamps or 1 amp if you would like. So we'll show that to you further on in the video also. All right. So These go into different types of cutouts, okay? So for each of these different types of meters, they will not all fit into the same cutout. So I just wanted to point that out to you. And so you can see there's a little different case style there. This is what we call a flat pack meter. And this one is microamps, 0 to 100 microamps. The meter, you'll notice, is very sensitive. And even though I have a wire across the terminals, the meter movement, the moving coil, is down way at the back down here. And so that needle is really, really long. So it doesn't take much movement for that needle to move. And so even though I'm damping the meter out with the shorted contacts, we're still getting a little bit of movement there. And I'll show you the difference. This one has also got a wire across it. It is also microamps. And when I move this one, you can see that the needle hardly moves at all. But this one, that needle moves quite a bit. Okay, I just wanted to show you that really quickly. And then, so these ones here along the front are what we call moving coil meters. And a moving coil meter has a wire coil inside. And if we can get that to focus up, let me see if I can do that. We can then look and see. Let's see if I can get that to focus. Yeah. So you can see down in there, just where the needle bends down, there's a little copper coil down in there. That's moving coil. The needle is attached to that coil. And then, of course, as you pass current through that coil, it's inside of a permanent magnet, and the needle moves per how much current you're flowing through that coil in that magnetic field. Now, so moving coil meters. This particular meter is different. This meter is what they call an iron core meter. Okay, and it is very, very sensitive because it doesn't have all of the physical weight of the copper wire, etc., being wound around a coil and then the needle being attached to the coil. The only thing that this needle is attached to is a little magnetic. It's not a magnetic. It's, let's just say it's a little paddle of metal that is affected by magnetic field. Let's put it that way. And I have, this is a 200 AC amperes 200 amps. And I have another one here that's AC amperes 100 amps. And I have the faceplate, etc., taken off. And I want to show you the inside of this meter. And the reason being is that now you're just passing a current. Let me get this up nice and close. And you can see the coil of wire. That is 14 gauge and 2 surface windings, okay, of 14 gauge wire around an iron core, open core. So what's going to be difficult to show you here is how the needle is attached to this paddle. And I'm going to see if I can get that right up. Yeah, so you can see the paddle down in there. And as I move this, let me see if I can move the needle with, and get that so I can move the needle. Whoop, I'm missing the needle. Come on, focus, that's it. So you can see that the top of the paddle is reflecting the light. And you can see the paddle moving there. So what happens is magnetic field is set up in that coil of wire, and that paddle then is being deflected based on how much current is flowing through that coil of wire. That particular coil of wire, or this meter, is set up that full scale deflection is 5 amps. So if you feed 5 amps through this coil, it will give you full deflection. And that coil of wire being 14 gauge will handle a continuous 5 amps. Okay. These type of meters are used in such things as power stations, um, on ships that have power stations, and such things like that, where they need to be able to measure very high currents. Also, in this one's particular case, it says here, caution, use only with external transformer. And that's to isolate the meter and its contacts, etc., away from a very high current source. So they put a transformer in there to cut the current down to a maximum of 5 amps to run through this coil. But they, let me put that down really quickly, but they change the scaling on the meter to match what the full scale current deflection is for that meter. Now, here's the second thing about this particular meter that is considerably different from your moving coil meter. This, and I will get my screwdriver here, this paddle down in here, let me see if I can get this up really close and get it to focus. There's a paddle right there, okay? And it is actually moving back and forth. I'll show you that. It's moving back and forth there. You can see it. Where it says 19 here, there, that's a magnet sitting down under there. And that paddle is in between the shell, the basic chassis part here, and a piece of metal where the magnet is sitting on. The reason for that is it's called it's for dampening the movement of the meter. If this was not there, this meter, just with air currents or me talking closely and the air coming out of my mouth as I'm talking, would cause this meter to just move like crazy. So even with me talking, you can see that that meter is moving. So that's me just giving a little puff. If I did that little tiny puff and it didn't have this magnet, that needle would shoot right across. So a little bit different, but we're also going to set this up and we're going to put some current through this and show you that you feed in a DC current, you're going to get a needle deflection. And if you want a really nice big meter on the face of some power supply that you're building, you can use this meter for that. So let me now show you. I will move these guys over here because the next thing I need to show you is shunts. So these all being voltmeters, they require a resistive element that you can measure the voltage drop across. And that, as I showed earlier, is typical of this right here. Okay, so what we have now, and I'll marry these two up. This is 0 to 50 amps, 75 millivolts to get full deflection. Okay, and this particular shunt, this is a shunt, and this shunt will handle 50 amps, and it will produce 75 millivolt drop across these terminals at 50 amps. And if you can see, it says it right there. It says 50 amps, 75 millivolts. And I've measured this shunt value on a bridge circuit for very accurate low ohm readings. And this particular shunt is 0.0015 ohms or 1.5 milliohms. Okay, and if you do your Ohm's law on that, you'll find that no matter which way you work out that Ohm's law with 1.5 milliohms and 75 millivolts, if you divide it, you're going to get 50 amps. Okay, so that's one type of shunt. I've used those shunts. Yeah, these are all the types of shunts that I've used with voltmeters. And the bottom line is that you can even use just regular resistors as a shunt. Here's a power resistor. This particular power resistor is 0.1 volts. It's not going to focus on this, but down here it says 0.1 volt, 0.1 volt. So that's actually a little bit high for resistance for a shunt. So in the case of this, I would probably put 2 or 3 of these possibly in parallel to get the resistance down. And don't forget how much power you're going to be feeding through these. Okay, that the higher the resistance and the more current you flow, the higher the power. And remember, it's a square. So, don't forget your Ohm's law and your power calculations, because you have to use your power calculations to be able to make sure you don't burn up your shunts. Okay. And we also have this piece of coiled wire here. This particular piece of coiled wire is 22 gauge. And it is 12 inches long, and I just wound it into a coil. Normally, you would not use a coil of wire that is insulated. You would use something similar to either a magnetic wire that has a lacquer cover on it, or you would use bare copper and then stand it off with non-conductive standoffs so that it can't touch the chassis or anything like that you're putting it into. A lot of shunts, for instance, this shunt comes mounted on a plastic mount, so you wouldn't have any trouble with that. So we're also going to show you this, and I have my American wire gauge chart, which I'll bring out over here. American wire gauge chart, I really like this particular chart. The reason being is that up here it says milliohms per foot. Normally wire charts will give you ohms per 1,000 feet. But when you're working in the milliohm range and pieces of wire that you want to use for a shunt, you don't want to be calculating. I mean, it's an easy calculation, but boy, this table is just so much better. So 22 gauge wire being here, that in 1 foot produces 16.14 milliohms for 1 foot of wire. So the reason I have this particular piece of wire, it's 12 inches from this cut end to this cut end, but you can see I've stripped some of the insulation off here. Well, when we hook this up to a meter and we apply voltage across this, and we're measuring that voltage drop, you can move, I'll move the alligator clips, because I'm going to use alligator clips for all of this. I can move the alligator clips along this open stretch of wire and literally tune the meter so that it's accurate. Okay, that's one way of doing it. Second way of doing it, of course, is to put a trim pot in the circuit, and we will show you that a little later also. Okay, so that's the introduction to ammeters, or if you like, voltmeters that are used for measuring a voltage drop to indicate how much current is flowing out through your load. One other thing I did want to point out quickly, you'll notice that said AC amps. You'll notice that this one also says AC milliamps, if that's going to focus for me. Let me see if I can. Oh, there we go. It's decided to do it anyway. Yeah, so this one has a bridge rectifier inside. And in the next segment, what I'll do is I'll have the back off of this and I will show you the bridge rectifier. So it's taking an AC signal and it's literally converting it to DC so that you can measure it on this DC voltmeter. All right, so let me stop this segment here. I will set up and we'll show you some bridges across the amp meters and some such. And we'll also be talking about how to measure the coil resistance of the coil of the moving coil meter, because we do need to know that in some cases, in some instances of use of the meters, especially when we're selecting series resistors, or we're selecting a shunt resistor, because and this is where you're coming into your series and parallel configuration of resistors. All right, so let me stop it there, and I will see you back here in a few minutes. I mentioned earlier that I wanted to show you in this meter the bridge rectifier. So this is milliamps AC, and they build in the bridge rectifier so that you don't have to worry about it. So I should get this over here where you can actually see what I'm doing. Okay, so let me bring this up, and you can see the bridge rectifier there. This guy right in here. And so just wanted to show you that just really quickly, that they can put the bridge rectifiers inside. If you're going to be changing a voltmeter, now remember, these are all voltmeters, but a regular voltmeter that says volts and you want to change it to amps, or you want to, sorry, if you want to take a regular voltmeter or a regular amp meter, such as this, DC milliamps, and make it so that you can measure AC, you will have to provide either a bridge rectifier or a full wave rectifier external to the meter. So I just wanted to show you that very quickly. And yeah, so I'll put this back together and I'll be right back, and then we'll look at doing some shunt across a meter. All right, see you in a moment. Okay, I have a amp meter, 50 amp meter set up. And what we're going to do is we're going to not measure 50 amps. Number one, because my power supply will only put out 3 amps, my bench power supply, that is. And secondly, this is also to show you how we can take this 50 amp meter, and convert it to show us 5 amps, or to convert it and show 3 amps full scale. Okay, so that, and this is so that if you buy some junk box or spare parts box meters off of eBay or an auction or some such, or you have some from old equipment, you can convert what you have into the meter that you need for your particular project. For instance, let's say I'm doing a plus minus 15 volt power supply that I'm making, and I want to put a nice little analog meter in there, then we can convert that. So I'm going to show you how to do that. Now, what I have set up here is I have the meter, have my power supply leads coming in here, and I have my shunt wire across here. Now, this shunt wire being 12 inches from the cut ends, okay, and that shunt wire is 16 ohms, approximately 16 ohms. Per the table, as I had pointed this table out before, a 22 gauge wire is 16.14 ohms. I do want to point out, though, that a lot of times this wire, its diameter or circular mill area is not always exact. So you're going to get a little bit of a difference in resistance than what the table is actually telling you. Okay, so if I then take my power supply and I have it set for 3 amps and currently 0 volts, and what I will do is I will put 3 amps across this, and you can see that it reads a little bit above 3 amps. So we've calculated what we need as a voltage drop, okay, across our shunt for this to read 75 millivolts full scale. remember now we have 75 millivolts full scale that we need. Okay, so also what you're seeing here is a discrepancy in where that meter is sitting, the needle is sitting there. And that discrepancy is just the resistances involved with the wires, these wires. Mind you, this is 14 gauge wire, so it's introducing extremely little resistance into this whole circuit. Okay, but we can move this alligator clip down and literally tune that meter to 3 amps. So let me show you how we do that. So if we move it down to half, you can see it moved down about 1 notch, 1 gradation. So we'll move it all the way down to there, to where I'm just barely touching the insulation there. And you can see we're just a little tiny hair above where, let me zoom that in for you. You can see where we're just basically right on the 3 amps. Okay, so that's how you can tune that. Now, of course, the second way you can tune also is by putting a variable resistor in. And how you do that is you cut the wire length less and put a variable resistor in series here. And that would allow you to manually tune it. Now, when you're talking 16 milliohms, that's pretty small. So you're going to be using a 100 ohm series resistor, and you're going to be tuning way down the bottom of that variable resistances wiper. Okay, let me turn this off. So now what I want to show you is this shunt hooked up, and this shunt is 18.6 inches long. And so when we calculate what that, how we're actually doing that, is we are for 5 amps. So what we currently have for 5 amps, we have a voltage needed at 0.075 volts, okay, full scale. And we need to put that over the top of 5 amps. So this is Ohm's law for you beginning folks. And what we're coming out with is 0.015 ohms. Okay, so that's what the value of this shunt needs to be for 5 amps to show 5 amps on the meter, full scale. And this is why we moved the connection point down, and you can see we didn't move it very much, about an inch here, to take it from 16.1 ohm, let's say, to 16.1 milliohms to 15 milliohms, roughly. So this is something you'll need to do, because if this meter is mounted in your front panel and your power supply box is fairly large, and you're going to have wires coming from wherever up to your meter, then you would have resistance in those wires, and you have to tune that resistance out. However, if it's low enough current, which it is in this particular case, and this wire is not going to get hot, then you can have literally your shunt right up onto the back of the meter. In most cases, the shunts are going to be producing quite a bit of heat, depending on how much current you're loading it with, and you want to be able to keep that stood off and away from other pieces of equipment and parts within your power supply. So one of the things I did want to show here is at 5 amps and 5 amps and the resistance and the voltage going across this, what is our actual power? Okay, so remember that for power, in this particular case, we'll use 0.75 volts, and we will square that. So we have to square that voltage, and we're going to divide that by the resistance, and that just happens to be 15 milliohms. Okay, I think you can see that. Maybe I'll make that a little bigger here. Let me make that just a bit bigger. So 0.015 ohms, okay? And that comes out to 0.375 watts. So a little bit over a quarter of a watt. So it's about 3/8 of a watt. So the wire is really, this wire at 5 amps is not going to really produce a lot of heat. However, 22 gauge wire is not what you use for 5 amps. So this is another thing you absolutely have to make sure of when you're looking at these wire gauges for 22 gauge wire at 60 degrees Celsius, 3 amps maximum. Okay? And you're dealing with usually room temperature or slightly above room temperature inside of a chassis. So that temperature may rise a little bit, but 60 degrees Celsius is pretty warm. So you don't want to go above 3 amps on 22 gauge wire and be safe. So this is something you must consider. Okay, the second thing I wanted to show you was this one, where now we're going to bring this meter to literally show us 3 amps at full scale. Okay, so let me just quickly disconnect this guy, and we shall connect up. I'm putting the same one right back again. Okay, we'll get this straight here in a moment. That guy, this one, and I think I can, let me get this guy down here so I can clip it on. Okay, this wire is 18.6 inches long. So this is how we can do a very simple calculation. So let's say you know what this shunt is going to be. You've got a shunt wire, you've calculated it out, etc. But you say, oh gosh, I actually want to read 3 amps. And you can't find your table or whatever. It's actually really simple. It's a straight ratio. And we can do this by going like this. We can say 0.064 equals, put a line underneath this, so it's ratios, 164 ohms, and that's for 12 inches. Okay, we need 0.025 because we've calculated that out, and I'll show you in a second here how we do that. We basically do the same thing here. We just substitute 3 into here, and it's going to give us 25 milliohms. Okay, so, and then this is over X, and of course this calculates out to 0.025 times 12, and that's divided by our 0.0164. And when we take the calculator and we calculate that out, 0.025 times 12 equals that, divided by 0.0164, and that equals 18.29 inches. So 18.3 inches. So 18.3 inches. Okay. That over there. So that's how we can go from one length of wire to what we need in another length of wire to go from 5 amps to 3 amps to show across the meter. So this is your scaling of what we can do and scaling the meter here. So let me turn this on. I just want to turn that down, and we'll turn that on. And then now when I bring this up, oops, it'd be a good idea if I turned the output on. There we go. So you can see it came immediately up to the 5. It's actually a little tiny hair over. So the resistance is off a little bit. Resistance of this wire is off a little bit. So now we're flowing 3 amps through this wire, and we could change the scaling on here using the tone software for changing the scaling, and put on a new faceplate, and with a 0 to 5, or sorry, 0 to 3, and now we have a 3 amp meter. Okay. So I just wanted to show you that. Now, another thing I do want to show you is this with a load connected in, or what we would consider to be a load. So right now, all we're doing is we're taking a voltmeter and we're measuring the voltage drop across this shunt. So here we have this 5 ohm resistor, and if we calculate this out, if I do 15 volts and 5 ohms, so 15 volts, our power supply is going to be 15 volts. This little plus minus power supply that you're going to make for your bench is going to be 15 volts. And you're going to put 3 amps through this resistor. So let's divide that by 5 ohms. And, well, you can see immediately that 15 divided by 5 equals 3. So now we can scale this meter so that when we're putting 3 amps out, or we're putting 15 volts out through our 5 ohm load, up to 5 ohms. So it depends on what your load is going to be pulling. In this particular case, I just happen to be using this 5 ohm resistor. If it was a 10 ohm resistor, it's obviously going to be half this, an amp and a half through the resistor. Okay, so let me show you that quickly. And how we can do that is we not do that. Let me see, that's not the one we want to move, that's the one we want to move. And we're going to put our negative lead on there. And we are going to put another lead from our load. The load can be a transmitter, a light bulb, something you're building on your breadboard, etc. Okay, and we'll hook that up. So now we have our load inserted, and we can turn this on, and I'm at 1 volt. So on my power supply, I'm showing 1 volt, and it shows 200 milliamps. So we're a little bit off on the gauge here because we didn't shift our value. Let me see if I move that down. No, that's going to move it up. So if I shift that there, I'm not going to really be able to dial that in close enough for this analog meter. So as I bring the voltage up, so I'm at 980 milliamps. So you can see it's a little low on the meter. And we're coming up to 15 volts. So there's 15 volts on the power supply, and we're producing 2.96 amps. So you can see we need a little tuning here. But now it's showing 3 amps, and we're pulling current through this resistor. Now, I don't want to leave that on too long. That is a 50 watt power resistor, but we're drawing 44.4 watts from what my meter is. So we're running this very close to its limit. So I'm just going to back that right back off again. Otherwise, that's going to get really hot. And if you go over that 50 watts, that means you're pushing a lot of current through that resistor, and you can burn the resistor out. And I have had that happen. And it really throws you in that your power supply is saying, hey, I've got, you've got an amp meter and a voltmeter on your power supply, and the power supply, you've got it dialed to 15 volts, but you've got nothing going to your load. And that's because that is hot. I just picked it up. That's because you've burned out your power resistor by trying to put too much current through it. In other words, your power resistor is too small and I'm talking about if the power resistor is your shunt. Okay? If your shunt is too small and you push too much current through it, you can burn your shunt out. Okay, I just want to let you know that. Plus, also, if you're doing exactly what we're doing here and you're testing your setup, you want to make sure that that power resistor can handle the current that's flowing through it. Okay, so let me go and put this part away, and I will bring in the microamp meter, and we will look at the microamp meter and set that up for measuring different currents and what we need to do in the way of setting that up. Now, before we do go, though, I do want to do one thing. I want to show you schematically what's going on here. So we have a load resistor. Okay. So let's say in my particular case where I built my linear power supply, that load is my ham radio. And my ham radio can pull, I believe at 100 watts, it pulls about 23 amps. My power supply, let's just say I rate it for 25 amps, but it can push out 30 amps, but I've rated for about 25 amps. And that's what I have all my controls set at. So just wanted to mention that. So this is your negative side or ground, if you like, of your chassis or whatever the negative side of the load is. Then you're coming out and you're going through your shunt here. And then this is your plus volts input. And of course, we're taking our voltmeter across here. Like so. Oh, by the way, one thing I did want to mention to you is that internally here, there is a resistor. There is a series resistor internally. And we'll talk about that when I go to the microamp meter. And that's to adjust the internal resistance of the meter so that it will take 75 millivolts full scale. Okay, but when we do the microamp meter over here, we will talk about that. Okay, so I just wanted to point out here what we're actually doing schematically. Okay, so let me get this out of the way and we'll bring in the microamp meter and we will have a look at that one. Before we move along here, I wanted to show you how to measure the resistance of these amp meters and determine what their internal resistance is. which then is going to give us what the full deflection voltage is. And you need that full deflection voltage so that you know what size shunt to use or what resistance of shunt to use. For instance, as we saw earlier, this particular one is 75 millivolts full scale across the shunt for 50 amps. Okay. If you want this to be 100 amps, then you would use a shunt that's half that value, which means it would be 750 micro ohms, okay, instead of 1.5 ohms. So that shunt on here is 1.5 ohms for 50 amps, Ohm's law. And you would double it to 3 milliohms if you wanted to change this scaling to 25 amps. Okay, so that's on this one. So this one's very nice. It gives you what that full scale voltage is, and you can work that out with your shunt. But when we get into some of these other meters, like this one, for instance, and if you look down in there, there's writing, etc. But it doesn't tell you what the full scale voltage is. So that's what we're going to look at. So if we take this meter, and this is in milliamperes, so it's not too bad. We can do, because it's milliamperes and my power supply can go to milliamperes, what I'll do is I'll put in 50 milliamperes maximum into my power supply, and I will make sure that the voltage is turned all the way down, and we can hook our power supply up to this. Thusly, okay, and we're going to turn on that output, and we're going to shift this over to a little bit lower, and you see how it went immediately up to 50, okay, and I'm at 0.1 volt. So because I have it set to max out at 50 milliamps, it's only going to go to 50 milliamps on this. So when you do this, make absolutely sure your power supply is set to maybe 40 milliamps, but my power supply is very accurate, so 50 milliamps, not a problem. Now what you do here to find out what the resistance, etc., is internally, and to find out what the exact voltage is to make that full scale reading, my power supply only goes to 2 digits. So I'm going to bring in my digital multimeter. I'm not going to use my bench one because it's too difficult. You can't see it. And I'm going to measure. We'll swing these around so we get a good reading. And we're going to measure across here, and we're going to see, if I don't slip off, we are going to see 61.4 millivolts full scale. Okay, so that's 61.4 volts full scale, 61.4 millivolts, 61.4 millivolts full scale at 0.05 amps, 50 milliamps. Let me move this out of the way. So we calculate that out, and I'll just turn that off. We calculate that out, and we have 0.0614, and this is fairly rough. It gets you in the ballpark. These are never exact, okay, because we have resistances in the wires to the meter and that kind of thing. So 61.4 millivolts divided by 0.05, and that gives us 1.228 or 1.23 if you like. So 1.23 ohms, 1.23 ohms. And that will be the coil resistance. So this tells you then that you need to get full scale reading, you need 61.4 millivolts across your shunt. So you saw on this meter, it's 75 millivolts across the shunt for full scale. This one's a little bit lower, but you also want to put your trim pot in so that you can trim any errors in your shunt resistance. Okay, so I just wanted to show you that. So then we have one that's 1 milliamp. My power supply is going to have a hard time dealing with 1 milliamp. So what we'll do with this one is we will grab the 10K resistor. I did measure it. It's very close to 10K, even though it's a 5% resistor. And what we'll do is we will take a 10K. You can use a 20K, you can use a 30K. I'm using a 10K because the math becomes rather easy, especially when you're dealing with a 1. So I think you can probably already see where this is going to go. I can just get that on there. Let's take that out. And we'll put this into here, and we'll put this into here, and we'll see what this does. Let me just, it doesn't want to cooperate very well. So there we go. So now what we're going to do here is we're going to make sure I am at 50 milliamps. So we'll leave that at 50 milliamps. I'm going to turn this down to 0, and I'm going to move over to the tenths on my volts. I'm going to turn the output on, and then I'm going to start turning this up. Okay, so that is not going to be enough. So we're going to change this over to volts, and now we'll go up by voltage. So as I crank this up, I'm going to go up to 1 milliamp here. I'm a little over there, a little under there. So we can go back to our fine condition, and we can move this up until that reads right on 1 milliamp. So currently, on my power supply, I have 22.4 volts going through a 10K resistor and whatever this has for internal resistance. So again, we're going to measure. Let me get this down a little bit. Can you still see that? Yes. We are going to measure the voltage drop across that meter. Remember, we got that 10K in series, so it makes a big difference here now. So see that? It's 12.25 volts at 1 milliamp. So it's gone up just a hair. Let's just turn that down a little bit. So as things start heating up from the currents that are going through it, you're going to get a little change. So that's more like it, 12 volts. Okay, so across that meter, we have 12 volts, full scale, at 0.001 amps. And of course, we can work that out pretty easily. So when you're dealing with amp meters, when you're getting down to these very small values, you want to put a series resistor in series with it, and then take the voltage reading across here, take the scale reading, do your Ohm's law, and you'll get the resistance. Okay, so that's that one. Then we come to, and a lot of times, a 1 milliamp, well, because this one's got basically 12,000 ohms of resistance on it, which it does. It has 12,000 ohms internal. You can put your meter directly, your power supply on it direct for 1 milliamp. So it'll take 1 milliamp going through it without any problem at all. But you wouldn't have known that. You would think, oh, well, this requires a shunt. And it's not saying anything. It doesn't say on here anywhere, oh, it takes 12 volts. So this is why you do what we're doing here. And now here we have microamps. And I did pick out a little resistor right here, and it's stuck on the bottom. And this resistor, I believe, is 22 22,000. I'm not sure what I picked. Yes, 22K, so it's 22,000 ohms. Now, because we're dealing with microamps, we got to get this resistor up pretty high. 22,000. Generally, if you're 50 microamps, 20 to 50,000 ohms. If you're down in the low microamps, like 10 microamps, I would go to 100,000 ohms to start. And then you can always work that down. So let me put this in series with this. And we'll see what this meter is doing. And now before I go putting any voltage on this, I do want to make absolutely sure. So 10K, 50 microamps, okay? Ohm's law on that. So let me just make sure that my voltage is turned off, and I'm going to turn up the current on this because we will need more than 50 milliamps. And I'm just going to set it at that. Okay, so turn this on, put this back over on volts, and we add 1 volt. So it's not showing, so I got to get back down here on, because we don't want to pin it like that. Let me put the fine movement down, and we can bring this up. I'm doing fine voltage control now in tenths of a volt, and we're going to bring it up until it hits 50 right there. Good, you can see that. Okay, then we're going to take our meter again, and we're going to measure that voltage. 82.8, close enough. 82.8. So 82.8 millivolts. So 0.082 volts at something. So at something is 0.000, or 50 microamps, right? So 50 microamps. This out of the way, that off. And we can calculate that. So remember, this is going to be your full scale reading. It won't be an exact voltage, because there's wire resistances, etc., that are taking place here. This resistor is close. It's like 10.01 ohm or something. But if you were just picking a resistor out of your resistor box, even at 1%, you're not going to get exactly 10 ohms unless you measure it. Or 10K, sorry, 10K. So we take 0.082, and we divide that by 0.00005, and we're going to come up with 1,640 ohms. So this is an estimated ohm, so we'll just put the little squigs in front of it. So your full scale here is going to be 0.082, and that's what your shunt is going to be set for, okay? The voltage drop across your shunt. So I just wanted to show you that quickly. When you get these junk box, or you get something off of eBay and it's not showing what your shunt value is, but you look at a meter like this and you go, yeah, that needs a shunt value. Unless you absolutely know for sure that you're doing like something in radio frequency or whatever, and you're never going to exceed 50 microamps, then you could use it direct. But other than that, you have to put a shunt across it. So I just wanted to add that in before we move along with the amp meters. All right, I will be back in a moment. So what I did here quickly, I just set up the 50 microampere meter here. Let me see if I can get that up a little further. And on my breadboard, I wired it into the breadboard here, and I have a series resistor trim pot here. And that trim pot is 1,000 ohms, okay? And then we have our 16 ohm shunt across here, and we're feeding our power supply through the shunt, through the load, and then out back to the power supply on ground. Okay, so that's the circuit. And so basically we're looking at this guy. So this is 1,000 ohms, not 100 ohms, it's 1,000 ohms. And this resistor is not there. And this resistance here with that shunt, if you remember, that's actually 0.016, I think it's like 3 or something, ohms for this particular shunt. And I haven't tuned the length here to bring the meter into compliance. But as we had mentioned earlier, we're somewhere in between here for voltages. So yeah. So I have a load resistance of 5 ohms, which will allow me to pull 3 amps at about 16 to 17, 15 to 17 volts. I didn't calculate it. So let me turn on the output here. Okay, so as we come up, so we're at 2.93, and you hear the click, and that's 3 amps. So that trim pot's actually sitting pretty good right now. Let me just zoom in a little bit on that. It's a little bit, I'll bring this over. Okay, so then if I take this trim pot, so the power supply is 3 amps. And let me see if I can just get my hands out of the way here. And we can trim this to show quite accurately the 3 amps. Okay, so I just wanted to quickly show you that putting a series resistor in here, trim pot into your meter circuit will help allow you to trim that out. It's changed just a hair there. There we go. You might be getting, no, that looks pretty good on the video. Not getting parallax or anything, so that's pretty good. Anyway, I just wanted to show you that. The next thing I want to show you is applying a DC voltage to this AC Simpson meter, moving iron core meter. So I shall be back in a moment with that set up and ready to show you. So here I've set up this Simpson meter, and if you remember, I said that it takes X amount of current to get full scale deflection. Now, I know the 200 amp meter takes, I don't know, 5 amps, puts it up in here somewhere, or 5 amps for full scale. So my power supply is only 3 amps. And yeah, so we're only going to be able to measure 3 amps, and we'll see where it comes on this particular meter. Let me turn on the output. I have it connected at the back side here, and I'm just propping it up with this resistor package here. So there we go. So that's 3 amps. And I'm going straight into the meter, so it's only the coil resistance inside that's stopping it. So I'm only showing 1 volt on my voltmeter, on the voltage for my power supply. I only show 1 volt, but it is at, actually it's not 1 volt, my error. It is actually showing 170 millivolts and 3 amps. And that's showing that. So at 60, I have 3. So we can obviously calculate that out. Also, we can calculate what the internal resistance is of that meter coil inside, and then we can adjust as necessary. So I just wanted to show you that quickly, that it is indeed a, even though it says AC amperes, it is a DC meter. And now this tells me um, what I need to know for actually using this for a large scale uh, meter, and change the scale. And remember, I mentioned earlier, and I will put it in the description, Tone software, TONNE software. They make several programs, and one of them is a program to rescale the face of a meter printed out on a laser printer or a jet printer, and then you can stick it over this, your original one, and now you have a new meter face. And of course, all the previous of this video is how to reconfigure the meter to read whatever you wish to make it read. So I just wanted to show you that. All right, and so that's the end of this part 2 of analog meters.